Welcome to my chemistry presentation. I'm B. Veeraraghuram from CSE AMLC section, and today I'm going to present to you about the solid state electrodes for analytic applications. As per the abstract, the increasing development of electrochemical variables and LOC sensors have created the urgent need of efficient and stable miniaturized reference electrodes, or for short, REs. Conventional liquid filled REs are not suitable for portable applications because of difficulty in trapping the solution in miniaturized electrodes and of high sensitivity to temperature and pressure variations. In this presentation, we investigate and compare different routes to fabricate solid contact REs, and we produce REs which are useful for calibration of nanostructured potentiometric sensors and the different stabilities at various chloride concentration and pH is also investigated. Starting investigation, the past few years have been growing interest towards portable and especially variable electrochemical systems. In particular, all solid-state potentiometric ion sensors have been extensively used for environmental monitoring and measuring the concentration of electrolytes in different body fluids for personalized healthcare. However, the realization of adequate and stable reference electrodes still represent one of the most challenging issues that prevent their commercialization. Although various strategies have been proposed in literatures, this problem is still far from a final solution. The AG-SAS AG3L double junction RE is most commonly used type of RE thanks to its excellent stability, simplicity, and non-toxic nature. Due to its popularity, it is most targeted RE for miniaturized system. In particular, the realization of all solid-state AGSAS, AGCL, REs represent one of the most attractive strategies since the elimination of the liquid junction eliminations problems of evaporation or sensitivity to temperature and pressure variations. A solid state exchange membrane doped with KCl or NaCl/AgCl is used to replace the liquid junction of conventional REs. Different strategies have been proposed, which include the impregnation of polymer with ionic liquid, solid doping of agar, or of a polymeric membrane. Here we have picture representation of solid KCl doping and impregnation of polymer and agar doping. In solid KCl doping, we take a polymeric membrane and the solid KCl and add them on the electrodes. Impregnation of a polymeric membrane, and ionic liquid together is deposited on the electrodes. Agar doping. In agar doping, we take solid KCl and agar solution and we heat them, and then it is deposited on the electrode. In this presentation, we produce different REs membranes to characterize and compare the electrochemical behavior in different conditions: agar, polyvinyl butyryl, polyvinyl chloride, ionic liquid, and doped PVC. The membranes then are used to calibrate lithium-ion selective electrodes, or ISE for short. The influence of chloride concentration and of pH on the stability is then investigated to help defining the best membrane of the different applications. And then going forward to the experimental methods, we take silver, platinum, and gold screen printed electrodes with a diameter of 4 mm as materials, and then we start the electrode fabrication. The chemical chlorination was performed in a 50 mm FeCl3 solution for 3 minutes. The agar membrane was produced with 0.8 grams of agar in 50 ml of 1 m KCl. After researching the boiling temperature, the solution was cooled to 65 centigrades and then spread over the electrode. In all cases, 10 UL of membrane solution was drop cashed on electrode. The membrane cocktail compositions are the following: 79.1 mg of PVB and 50 mg of NaCl in ethanol for PVB, 0.4 grams of PVC in NaCl saturated tetrahydrofuran for PVC, 0.1% of IL and 33% of PVC powder, 66% of waste to ethyl Sebacate in 0.5 ml of THF. For the PVC membrane doped with ionic lipid, 5 replicas were produced per sample type. Li plus IACs with nanostructured solid contacts were fabricated as described elsewhere. The fabrications were performed by subsequent LICL additions. Morphological and electrochemical characterization. A two-electrode setup was used in all parametric measurements during a double junction AG/AgCl Re from Metrohem, filled with 3M KCl and lithium acetate and internal and external solutions respectively. The cyclic volumetry was performed in a three-electrode setup. Then, SEM images were obtained with a Merlin microscope in SEM mode using in-lenses detector. The table below is a representation of sensor parameters of an Li plus IAC obtained with different REs, no membrane, PVC, agar, PVC, and ILPVC and DJ or double junction are recorded respectively. This is the graphical representation obtained during the experiment of no membrane, PVB, agar, PVC, ILPVC respectively. These are the SEM images of different reference membranes collected during the experiment: agar, PVB, PVC, and ILPVC respectively. Now let us go ahead with experiment results and discussion. Different ion exchange reference membranes are proposed and compared in this work to improve the performance of simple solid state electrode of Ag/AgCl, solid doped agar, solid doped PVB, solid doped PVC, and IL doped PVC. The fabricated REs are then tested for the calibration of Li plus IACs based on nanostructured solid contacts. A typical calibration example is given for ILPVC RE. All calibrations are performed by subsequent LICL additions. All sensors parameters obtained during different all solid state REs are given in the table below. In comparison with conventional DJ, AG/AgCl RE and with a chlorinated planar AG/AgCl RE without exchange membrane, it is worth noting that PVB, PVC, and ILPVC REs exhibit quasi-Nernstein response. The ILPVC and PVB membranes have a limited drift until reach high concentrations, for example 10 to 2 or 10 to 1 m. The PVC membranes shows the most stable potential at low concentration. Only at high concentration they start to exhibit sensitivity to chloride ions. The lowest permeability of PVC membrane is probably due to the more compact structure with respect to the other solid state REs. On contrary, the different agar samples show significant deals in both directions, which limitedly reproducibility. This behavior can be justified by considering the low elastic modules of this material that makes it very permeable and prone to detachments as evident. The figure of pH on the Re potential was also analyzed. It is possible to observe from the figure that in all cases the presence of Re membrane drastically improves the stability in different pH and reproducibility among different replicas. As from the previous test, the agar membranes show the poorest behavior. PVB, IL, PVC, and PVC references membrane drastically enhance the Re stability and reproducibility at different pH. In conclusion, the PVB, PVC, and IL-PVC membranes offer good stability and reproducibility with subtle difference depending on the application and on the pH of the working solution. I thank you for hearing out my presentation about all solid state reference electrodes and its analytic applications. I hope you have understood at least a bit about the solid state reference electrodes and the experimental procedures and the graphical representations I have been through. Hope these are implemented thoroughly and very fast in our future uses so that the technology and the electrochemical ware can be used daily. Thank you.